Section 1.2 is going to have us evaluating limits, no longer relying on a graphical or a numerical approach, but instead really evaluating these limits analytically or algebraically. Now, initially you see a whole slew of limit properties here, kind of taken right from your book. And for the most part, the first, kind of all but the last two, you might kind of summarize verbally as just saying limits somewhat behave like you want them to. So the limit of a sum or difference is the sum or difference of the limit. Same thing with a product. The limit of a product is the product of the limits. Constants get carried along. The powers or radicals or rational exponents, kind of look at those middle three. So essentially the limit of the power, you can take the power of the limit. Limit of a quotient is the quotient of the limit. So you have a lot that we're going to just kind of recognize this is sort of what you would instinctively do, and we get to do that. The last two are really going to get at the idea that essentially is going to tell us that when we get there and we're evaluating limits, when you think about nice polynomial functions, they're continuous everywhere. So any place that I want to start to investigate a limit, because these functions are continuous everywhere, anytime I'm evaluating the limit at a specified point, the left limit's going to equal the right limit is going to equal the value at that point. And so that's going to tell us that we're going to get to evaluate a polynomial function. If we're at some point C here, we're going to get to evaluate that limit by just essentially subbing that in and doing direct substitution into the function. So that's what that one is saying. And the last one is really the same thing, except obviously I'm talking about a rational function. It's saying as long as you're not at a location that's not included in the domain. So if I have some sort of rational function, let's say I have maybe a vertical asymptote here, but any other location that is included in the domain, if it's a rational function, is going to be sort of the same idea here. So at any other location, if I'm interested in the limit, as long as I'm not at a place where the x value, the input value that I'm interested in evaluating the limit at, as long as I'm not at a location that's not included in the domain, I will be able to do direct substitution once again. So again, as long as I'm in a place that's in the domain, if I'm interested in evaluating this limit at as x approaches c, well, that's just going to be this function evaluated at the point c. So that's really what those last two are saying, and we'll kind of get there, I would say, in more detail as we move in through the section. But first, we're just going to apply some of those initial properties here with this example taken from your Sullivan book. So the limit as x approaches 3 of g of x plus h of x. So essentially, and we may not write this out every single time, but what we know is that if I have a limit of a sum, I can take the sum of the limits. So the limit of the sum is the sum of the limits. So this is going to equal the limit as x approaches 3 from the left of g of x plus the limit as x approaches 3 from the left of h of x. And that's kind of how all of these will go. So I may not write out those details every time. We may just kind of go to this particular step. All right, so let's take a look on the g of x function there. So as I am maybe approaching 3 from the left, I'm getting closer and closer to 3 from the left here on g. And so that limit is going to 6. And then as I approach 3 from the left on the h of x function, so approaching 3 from the left on my h of x function, that is approaching -2. So of course my final answer here, my 6 minus 2, is just going to give me 4. All right, so let's take a look at these next two. And again, in a really similar way, the limit of a quotient is the quotient of the limit. So let's kind of go right to this. The limit as x approaches as x approaches 3 of f of x. So now we're focusing on the f function. So as I get closer and closer to 3 from both sides here on my f of x, that's getting closer and closer to 0. And then on my h of x function, as I get closer and closer to 3, now from both sides for the overall limit, this is going to negative 2. So of course my 0 divided by negative 2 is going to be 0. And then the last one just has a whole combination of, we have the difference of the limit of difference is the difference of the limits. The constant multiple gets carried along, and the limit of a rational exponent is the rational exponent of the limits. We have all these properties. So let's apply it relatively instinctively, I think, for most students. So the limit as x approaches 3 of f of x. So that's the one that we just did, and we saw that that was 0. And then we have our minus 2 times the limit as x approaches 3 of h of x. Okay, we've done that one also, and that was negative 2. And then this whole thing here is raised to the 3/2 power. So we end up with 4. And the 3/2 is really like a square root cubed, if you want to think of it that way. So of course this is just 2 cubed, and our final result here would be 8. All right, so those are just some basic limit properties. Now what we want to get into is kind of an extension of these last two properties that you saw, saying essentially both the limit of the polynomial property and the limit of the rational function property. Both of those are really saying that if the function is continuous, then you're going to be able to just, if the function's continuous at that point, you're going to be able just to use direct substitution. So that's going to be kind of our first instinct when we look at evaluating a limit, is we're going to think to ourselves, well, can I just apply direct substitution? So the first thing we're going to do is we're going to try just that. So we're going to try our direct substitution. So in other words, essentially, we're going to try to take this limit as x approaches c of f of x. We're just going to simply try to evaluate that by subbing in c. So notice here, my key phrase, I guess I would say, in this case was try. Okay, so what do we mean by try? Well, of course, we're going to do that, but we have to be on the lookout for some problems that are going to indicate to us that we can't actually proceed quite so easily. So that's going to happen in situations where f is not continuous. So if f is not continuous, so if f is not continuous at x equals c, then this direct substitution, which seems great, like I know I can use it for polynomials, I know I can use it for rational functions as long as it's not at a place that's not in the domain. But if the function's not continuous at that point that you're evaluating the limit, then you can't use direct substitution. So how are you going to know that? That's the question. How am I going to know if direct substitution fails? So in particular, what we want to be on the lookout for, so in particular, these are the things that we want to watch for. And the first one is going to be, well, that first or second doesn't really matter, what I'm going to call cutoff points of piecewise defined functions. So of piecewise functions. So places where a piecewise function is changing definition from one function to another. So cutoff points of piecewise functions are always going to be things that we have to investigate more closely, because it's kind of anything can happen there. It can be continuous, it can be discontinuous, and all sorts of specific types of things can happen there. And then the other one is always kind of our biggest culprit, is going to be zeros in denominators. This is always a big problem for us in lots of areas, right? So division by zero is not defined. So in these two situations, the thing that you want to think about here initially and be cautious of is that these two situations do not mean that the limit does not exist. So I got a double negative there. They do not mean that the limit does not exist. Okay, what they mean is we have to develop some techniques to handle these limits. So I'll just put in parentheses here. We're going to develop in these next set of examples here, we're going to develop techniques to deal with these situations. So these situations being these cutoff points of piecewise functions and then zeros and denominators. Okay, so let's take a look at our first example. Limit as x approaches 2 of negative x squared plus 3 over x plus 1. So direct substitution here is the way to go. I only see one, that middle term is a little rational function, that 3 over x. And so x equals 0 is not in the domain, but this is the limit as x approaches 2. So I get to just do my good old direct substitution. So negative, and then 2 squared plus my 3 over 2, and then plus 1. So we're going to have negative 4 plus 1.5 plus 1. So 2.5 minus 4. So be careful here. That first term is negative. That is a common mistake for all levels of students here. This negative here was never included in the squaring. So that first term is negative 4. Okay, so we're going to end up with our limit here as being negative 1.5. All right, so let's look at another example. So this next example is a piecewise function, and it's actually one that we've already looked at the graph of before. And so I am going to attempt here to pull up my graph of that. I took a little screenshot. Okay, so we've done this graph before, and so this was back on, what did I say? Oops, on like the top of page 6, I think, or something. I have it written down here, but I've just covered it up. So here's the graph. We did this one last time when we looked at some limits. So what I want you to realize is when you have a piecewise function, if you're being asked a limit that's not about a limit at a cutoff point, like look at this function, the only place where something kind of funky happens is at x equals 1. Everywhere else it's continuous. It's a line before 1, it's a parabola after 1, something weird happens at 1, maybe we can see what it looks like, but we just kind of need to have that mental idea in our head, even if we don't have a perfect picture of the graph. So on something like this, we can still use direct substitution because I'm not looking at the limits as x approaches 1. That's going to require us to delve a little deeper. But in this case, I'm good. So if I just sub in my direct substitution, in this case, I'm defined for values x greater than 1, I'm simply subbing in my 2 squared plus 1. So 4 plus 1 is 5. And we can see over here on our picture, that's exactly right. The limit as x approaches 2, it's getting closer and closer to, and actually it's continuous right there at 5. Now, if we start getting into limits as x is approaching the place where it changes definition, the cutoff point of the piecewise function. So if I was to ask on this same function, the limit as x approaches 1, this is where we're going to have to be a little bit more careful. So when you have, in these situations, when you're looking at the limit as x approaches c, where c is that cutoff point of a piecewise function, then we're going to have to know to do what we did visually when we did these with the graphical technique. So we're going to have to know to do this. We're going to have to look at the limit as x approaches c, and we're going to have to look at it from the left, and then we're going to have to look at the limit as x approaches c, and we're going to have to look at that then from the right of f of x, that limit. And so what we want to do when we're done is compare those two results, exactly what we're doing over there visually. So if when I'm done, so if these two are equal, then that number, so let's give it a number here. So let's say these two are both equal to, let's say, L. Okay, then that implies that our limit as x approaches c of f of x would be equal to L. Okay, but if those two are not equal, so actually, you know what, I'm going to write this a little bit differently. It's exactly the same thing. Let's just maybe kind of pose it this way. So let's say we look at these two and we ask ourselves, are those two equal to each other? Okay, so here's the situation then. If they are equal, then that number, whatever it is the limit. Okay, so it's the limit that we're looking for here. If those two one-sided limits aren't equal, then the limit does not exist. All right, and that's exactly what we've been doing. That's the definition. It's just we've been doing it graphically. Now we need to do it algebraically or analytically. So I am not stating anything new. I'm just stating kind of how we're going to write this out algebraically. So the first thing I'm going to look at here then, if I'm asked for the limit as x approaches 1 of g of x, I'm going to look at the limit as x approaches 1 from the left, and then I'm going to have to look at the limit as x approaches 1 from the right, and then I'm going to have to decide if those two are equal or not. So let's slide this down so we can see our function up there. So the limit as x approaches 1 from the left. So coming from the left of 1 is coming in from values less than 1. So I am plugging into negative 2x plus 4. So I am subbing into negative 2 times my x value is 1 plus 4, and that's equal to 2. All right, now I want to do the same thing, but I want to look at the limit this time coming from the right of 1. So right of 1 is values of x that are greater than 1, so I'm plugging into the bottom rule there, x squared plus 1. My x in this case is 1, so 1 squared plus 1 is 2. And I hope you're looking at the picture on the right-hand side. This is exactly what we looked at before. We're just doing it analytically. I just don't have to take the time then in this whole thing and like do the full graph and everything. I don't need to do that. Those two are equal. So now I know that my limit as x approaches 1 on this g of x function, this is equal to 2. Okay, and that's how we're going to evaluate limits of piecewise functions. So next time, as you can see, I have another example for us to look at, and then we're also going to look at another situation involving zeros and denominators, and real specifically, we're going to talk about something called an indeterminate form of 0 over 0. So that's where we'll pick up next time.